Okay, so let's continue our lecture on vibration for axial bar equation or motion. Um, Today I will cover only several parts of this lecture. I won't go very deeply all the way to very complex method because uh, during this semester vibration should be just introduction but not should not go too deeply. Okay, let me recall the equation of motion that was illustrated or derived by the previous lecture. Here, let me explain some variable and parameter again to recall what you have learned before. So this equation is for a bar like this, and so this equation is to find the displacement u at particular coordinate x and at particular time t. So the x-axis is in this direction, just one dimension. Um, so let's see one point at coordinate x here. When there is external force applied on the bar, it can displace to another point. And so for this point, display to this point, and another point here displays to another point here. Okay, so from the this blue and red here we call delta H, and from this blue to this red we have delta U. Okay, then the delta U over delta H is called strain when we take delta H approach to 0. Then we have the definition of instantaneous strain at the particular coordinate epsilon equal to partial U over partial H. And the displacement at this particular point also change in time if the bar is applied by force in function of time. So the displacement U, the displacement U is a function of H and time. Okay, so here is the final equation of motion, um, where rho is density, mass per volume. So rho is m over the volume v, and a is the cross-sectional area. So like this, and then a is cross-sectional area here. And E is Young modulus. So if A is uniform and the density is also uniform, and if the material is on if the bar is composed of one material type only, then E is constant. Then this equation can be rewritten as this, where alpha is the ratio of Young modulus and density. Well, so we can see this equation has a very special form that partial derivative with respect to time only can be equal to partial derivative of that function with respect to h only. So the solution can be imagined to be a combination of two different functions. One function is function of h only, and another function is function of time only. So use this kind of uh, okay, this kind of expected solution is found using method of separation of variable. Okay, so this kind of function is a form of separation of variables. Then take partial derivative twice with respect to time and twice with respect to age. Then we can have this equation, this ratio equal to this ratio. So this ratio can be any number p. Okay. Then we can solve separately for the function h, capital H, and for function capital T. Okay. So the homogeneous solution for T takes this form, and the homogeneous solution of capital H take this form. Okay, because the characteristic equation has complex roots. Okay, it's purely complex root. So the solution take the form of trigonometric function for both capital T and capital H. And because this ratio can be any constant p, so p can be any number. That's why the solution, the total solution of the equation of motion is the sum of the solution for each value of p. Okay, so here is the total solution is the sum of solution for particular p. Okay, and then we can use well, so-called boundary condition. So EBC is boundary condition for this point, and NBC is boundary condition for this point. Okay, so at this point, at h equal to 0, so this 0 is from h. At h equal to 0, the displacement is always 0. Okay, and for the boundary condition at this point, uh, the strain at this point is always 0. So strain means the partial derivative of u with respect to h. Okay, computed at h equal to l is always 0, right? Okay. No, sorry, I should say, well, um, because this is for free bar, so I should say in another way, this free bar, there's no force applying here. So the boundary condition at this point is equal to 0 because there's no external force. So this expression is from force. Uh, E times epsilon here is the stress, and the stress time cross section A is force. So there's no external force here. Okay, and then using these two boundary condition, we can eliminate some parameter like Ci. Yeah, Ci is 0, and so we wait. Okay, yeah. So we substitute 0 for h, Then we can have this and set it to 0. Then we got ci equal to 0. And using the boundary condition at this point, then we substitute this term equal to 0. Then we can find value of pi equal to this. Okay, so pi is multiple of pi alpha over 2l. So I is integer number. Then we have the solution, the time dependent solution u h of t, u of h and t like this, and then we apply the initial condition. Okay, boundary condition, we deal with condition at particular coordinate h, and then we can use initial condition to reduce other parameter. Okay, or to find other parameter. uh, for example, here ai and bi. Yeah, for free bar free vibration, general solution only take this form, which means uh, the b term is 0. So it can be illustrated here. Okay, so look at the displacement at initial time for t equal to 0. T, so at the start, all the bar here has the length, has a certain displacement. For example, let's say at initial time, we we pull the bar to extend to the length. Wait, look, let me see. If this called L0, then let's say at initial time we push the bar to this length. Oh, sorry, let me clarify what is L, what is L0. I see. Okay, so L is the length of the bar without any external force, any displacement. Okay, but zero here means at the initial time we stretch the bar. Okay, we pull the bar up to this point, so it has length L0. Then the displacement u, okay, displacement u should has um, so the okay you add the displacement, you add the value L should have L0 minus L, because this is the displacement u at L at initial time. Okay, this distance. Okay, um, uh, what if we want to find u at any value h at time 0? So actually it is expressed by this term. Okay, we can do the proportional method. um, so just let me verify by substituting h by l. If I substitute h by l, then l cancel. Then we have L0 minus L is the displacement, which is this, right? So the initial condition for displacement for any value h is expressed by this, and then the uh, time derivative of the displacement at time zero, because at t equal to zero, when we pull it up to this point, we there's no velocity, so just pull it and hang it there. When we start the time and then we release it, okay, so there's no initial velocity of the displacement. That's why this condition is zero. Okay, I mean this time derivative is zero. So first, using this condition, then we have bi equal to zero, and then by using this condition, we can have this equal to this. So this one is like line equation, right? um, it just equation like this, line like this. So here is u at h at zero, and here is, okay, so here is h, and so this one equal to the sum, the infinite sum of this term. This means we can imagine that this function is periodic over L. Oops. Yeah, because here from 0 to L, yeah, we can assume that this function is periodic over the period. Should I say period? Mm, L or 2L? Sorry. Look at this. Look at this one. If I want to find the period, is 2 pi over pi over 2L. Oh, yes. Period on X. Okay, period on X. Uh, so it become 4 pi, 4 pi, no, pi cancel, become 4L, right, 4L. Okay, so imagine that it has period over 4L, so I should, yeah, this function reappear at the 4L like this. Okay, let me draw another place. So I have 1L, 2L, 3L, and 4L. Okay, 1L, so here is 4L. So if a function is like this, yeah, you can take, so it's 0 like this, and then 4L here, and then it start like this. But anyway, because the left hand side has the boundary from 0 to L only, then over this period, uh, it just like the integral valid only from 0 to L. Okay, um, so this equation is a form of Fourier series. That's why the way to find a is to take the integral from 0 to L. Okay, then finally we can have a equal to this term, and then the total solution, the final total solution u of h of t, is expressed by this. And the next part is the bar axis, the axis bar again, but uh, the bar is fixed and free with apply force at the, okay. So here is there's no apply force, but here has applied force governed by f0 sine omega t. Then the initial condition, boundary condition at this point is still the same, but the boundary condition at this point now at the end point here there is external force. So this expression represents the force on the endpoint here. So must be equal to the external force or the applied force. Um, so from the boundary condition at h equal to 0, again we got the a1 is 0. Yeah, a1 equal to 0. And using the boundary condition at this point, we get a2 equal to this. So the final total solution has this form. Okay. So let me remind a little bit that the equation has four parameters. That's why we need four conditions. Two parameters from the second derivative of the second partial derivative with respect to h, and the other two parameter is from the second partial derivative with respect to time. So two condition from boundary condition and two condition from initial condition in order to find all the four parameters. And the next part, uh, we consider the motion of the base. That means if the base has motion, it means this point has motion. Okay, and the motion is described by u at h equal to 0 and in function of time, okay, equal to u0 sine omega t. Okay, so this displacement u here means the movement itself of this space itself. So this point has movement and the bar itself vibrate, it can displace, and then the total displacement would be governed by the equation that need to use this boundary condition, okay, and other boundary condition. So now the boundary condition at h equal to 0, okay, u of 0 of t equal to sine because this become 1, this becomes 0, so a1 times this and equal to u0 sine omega t. Then a1 is just u0, right? For the boundary condition at this point, again, in this case, there's no applied force. So the condition of applied force is this form and it is set to 0. Then we can have A2, okay, A2 equal to U0 times this term. So the final total solution has this form. Okay, A1 is U0, A2 U0 times here, and the function of time is must be the same as uh, the moving base, the motion of the base. Okay, is there any question? Từ bây giờ từ thì tiếp từ.
No, it's fine. Thank you.
Okay, so I think that's enough for introduction to vibration, especially for the continuum continuum element. For the in this case, we talk about axial bar. Then I would like to end the lecture of vibration for the continuous system here. Next week we will have a different lecture. Okay. So, any question from Cambodian student?
No, for the moment, teacher.
No question. Um, well, so I have question. Is it too difficult?